You ever stop and wonder what's really happening inside your computer when you've got a video streaming, emails popping in, and like a dozen browser tabs open all at once? I mean, it seems like magic, right? But underneath it all is this surprisingly elegant system for sorting and delivering all that data. So today, we're going to pull back the curtain on the internet's internal delivery service.
Yeah, so that's the big question, isn't it? How does your machine know that these incoming data packets belong to Netflix, while those are for your email, and that other bunch is for the cat video you've got playing in another tab? Think about it. It's this massive traffic control problem, and it's happening millions of times every single second.
Okay, so to really get a grip on this, let's use a great analogy. The best way to picture the internet's data delivery system is to think of it as a massive, and I mean incredibly efficient, postal service. All right, so here's how this breaks down. Your computer or your phone, that's a house. Now, all the different applications running on it, Netflix, your browser, your email, those are the kids living in that house. The data they're sending back and forth, those are letters and envelopes. The postal service that gets a letter from one house to another, that's the network layer. And the parents, Ann and Bill, who stand at the door, sort all the mail and hand it to the right kid, well, that's the transport layer.
And this is the really crucial part. You got to get this distinction. The network layer, using what's called an IP address, only cares about one thing: getting the data packet to the correct computer, the right house. But once that letter arrives at the front door, the transport layer takes over. Its job is to look at that data and deliver it to the specific application that's waiting for it, the right kid.
Okay, so we get the what. We need to get the data to the right app. But how does that actually happen? Well, it involves two key processes with kind of fancy names, but trust me, the idea behind them is super straightforward.
All right, first up is this term, demultiplexing. I know, it sounds super technical, but don't let the name scare you. It's just the official term for what the parents in our analogy do. It's the simple act of taking a big pile of incoming mail from the mailbox and sorting it, making sure every single letter gets to the right person, or, in our case, the right application.
And the way it works is actually super logical. So picture this. A datagram, our little digital letter, lands on your computer. Step 1. The network layer checks the IP address and says, yep, this is the right house. Step 2. Then the transport layer looks at another piece of info on the envelope, the port number. Just think of a port number as the specific kid's room number. Netflix gets one room, your browser gets another. That's how it knows exactly where to deliver the data.
Okay, so things get even more interesting. It turns out this digital postal service doesn't just have one type of mail carrier. It has two very different delivery people, and they each have a really specific job. Let's meet TCP and UDP. These are the two main transport protocols we use literally every day.
And this slide just lays it out perfectly. On one side, you have UDP, the sprinter. It's all about speed. It's fast and loose. It doesn't wait to set up some formal connection. It just sends the data. The catch? It doesn't guarantee every packet gets there or that they'll be in the right order. This is perfect for things like video streaming or online gaming, where a dropped frame here and there isn't the end of the world, but lag is. Then you've got TCP, the marathoner. It's slow and steady, super meticulous. It sets up a connection, guarantees every single piece of data arrives, and makes sure it's all put back together in the right order. This is absolutely essential for things like email or loading a web page, where you need every single piece of the puzzle to be perfect.
But that begs the question, right? Why on earth would anyone ever use a service that's described as unreliable? Well, what seems like UDP's weakness is actually its greatest strength. See, there's no delay, no handshake to set up a connection, it just sends. It's super simple, so your computer doesn't have to keep track of a complex connection. Its address label is tiny, meaning less wasted space. And here's the kicker, it has no congestion control. It just blasts data as fast as the network will allow, which is exactly what some apps need.
So what's the secret sauce here? How do these two protocols, TCP and UDP, achieve such totally different results? Well, like we hinted at before, the real secret is in how they address the data. It's all about what information they write on that digital envelope.
Well, for UDP, our sprinter, it's all about simplicity. It only needs, get this, two little pieces of information to do its job.
This whole idea is called connectionless demultiplexing. UDP only cares about two things: the destination house, which is the IP address, and the destination kid's room, the port number. That's it.
It doesn't care who sent the letter. If it's addressed to that port, it gets thrown into that application's mail pile or socket. Simple, fast, and really efficient.
Now, TCP, our careful marathoner, it's a completely different story. It is way more detailed. In stark contrast to UDP's 2 items, TCP uses 4 to create a very specific, dedicated connection.
And this is called connection-oriented demultiplexing, and it is a total game changer. TCP tracks 4 things: where the letter is from, the source IP and port, and where it's going, the destination IP and port. This 4-part identifier creates a unique, dedicated conversation channel. It's how a single web server, using just one main port, like port 80 for web traffic, can have thousands of simultaneous, private, and totally reliable conversations with thousands of different users all at the same time, without ever mixing up their data. Okay, so we've established that TCP is like our certified mail carrier. But what's in its toolkit? What does it actually use to make sure that every single letter gets to its destination safe and sound and in exactly the right order? And this question right here, it just perfectly sums up the whole challenge. The internet itself, at its core, is an unreliable channel. It's a wild place. Packets get lost, data gets corrupted, things show up all out of order. TCP was literally invented to solve this exact problem.
And here's how it does it. This is the toolkit. First, it uses a checksum, which is basically a way to check if a letter got smudged or corrupted in the mail. Second, for every packet it receives, the receiver sends back an acknowledgement, an ACK, which is like a little postcard saying, "Yep, got it." Third, it uses sequence numbers on every packet, so even if the letters arrive all jumbled up, they can be put back in the right order. And finally, there's a timer. If the sender doesn't get that "got it" postcard back in time, it just assumes the letter was lost in the mail and sends a copy. This whole combination creates perfect reliability out of total chaos.
So when you boil it all down, it's not really a battle between speed and reliability. The true genius of the internet's design is that it gives applications both options. It's this flexible system with different shipping choices for different needs. And that core principle is what allowed it to scale into what it is today. So the final question is, as you're experiencing this right now, which delivery person do you think is at work? The fast sprinter or the steady marathoner?